Recording is on.
Okay, great. So, as I said, I'm the founder of Creators, which is an applied research in autonomous systems startup here in Spain, and also I'm organizer. Sorry, I'm organizer of the Barcelona Rust meetup. So, if any of you guys wants to make something there, we can keep in touch and see what we can make. So let's start with the basics. A virtual machine in Rust. So basically, a virtual machine has three main pieces, a part of all other stuff, which basically are a bytecode, a program counter, and also the operations itself. So the bytecode is basically a vector with bytes. So each byte has some kind of semantics that we are going to talk about them right now. It has a program counter where it tells you where are you on the bytecode, so that way you can go through the bytecode, which will be the program. And then we have our operations, which are the semantics of each of the bytes. So for example, in this case, the 0x01, it's basically an operation for loading a constant into the stack. It gets a literal value from the bytecode itself, and it loads into the virtual machine stack, which is a part of the virtual machine memory. So if you take a look of what an actual SRUG for the virtual machine looks like, basically has three main pieces, which is the memory manager, which we will not dive into that because it could be another talk by itself. Then we have the bytecode, which will be this vector of bytes, and also the program counter. If everything is going right, like, can you hear me well? Okay, perfect. So basically, if we take a look of which methods are implemented in the virtual machine, we have basically the run where we made like the whole prelude, which is loading everything on the virtual machine context, which will be like their definitions, the context that is needed to run the virtual machine, and what you expect to be loaded while you're running the machine. And then we have the run bytecode method. This run bytecode basically it's a recursive function which returns a future, and basically it iterates over the bytecode until it reaches the end of the bytecode, and then we get the current bytecode position based on the program counter. So that way we iterate through the whole bytecode. Then we process each operation based on the current byte. So right now the virtual machine has 24 operations or opcodes, load const, load bar, store bar, and all of them. If we take a look to load const, which is the most basic one, basically we have the operation code, the data type that we want to load into the virtual machine, and then the bytes data of the data that we want to, the actual value that we want to load. So if we take a look of how it is implemented in the actual code, basically we have our program counter and we increment by 1 to go from the operation code to the actual data type. Then with that, we get the actual value of the actual length of the value that we want to load into the stack. And then we convert those bytes into an actual value. So for then pushing them onto the stack and incrementing by 1 the program counter. So these ways we will end up here, which will be the next operation. And we will start like making this whole through the whole bytecode until we reach, as we have said, to the end of the bytecode. So if we think about a program, it doesn't necessarily mean to be on a programming language specifically, but a conceptual program that takes, for example, two numbers and performs an addition to store on a variable. On a bytecode could look like this, which is basically loading the two constants into the stack, then performing an addition operation, and then storing the value into a variable x. Let's see how this runs or how this works. So if we go to VS Code, here there is this program called written in Ego, which is a very basic programming language that I built for compiling to actual bytecode for the virtual machine. So if we run this bytecode, it doesn't make anything because we don't print any value. But if we run with -d flag, we can see here all of this is for the actual language stuff, but here we have the bytecode itself and the runtime execution. So here we will have load const of the two values, which will be these two, then perform an addition, and then storing this variable into storing this result into the x variable. So this way we'll we will start building a whole program. For example, this was a very basic example, only assigning a variable, a value to a variable, but we can use also, for example, loops. So if we run this again, we will have a very more large program, which will make basically the same thing: loading constants, storing variables. In this case, it loads the constant 0 to a variable count, and also load const print to then call the print with the loop argument and starts making the whole program. In the while loop, it's basically a game of jumping if a value is false and then trying to go again. So we will start going through back and forth of the tape until we reach a condition that make us go forward. This is great, but this is a very basic virtual machine, so we can perform very basic operations. If we wanted to build a more complex behavior, we should need a standard library or something like that. So this virtual machine has a standard library, which a file system, I/O, HTTP, net, OS, and many more modules, which basically are implemented, and you can use them with the import operation code. So the import operation code, basically based on a string that you pass to the operation, it gives you a native module type, and then generates that native module type definition, which is an struct in Rust. So we have, as I have said, many different modules, and we generate an struct for each of them. So let's see how the standard library works also in the code example. If we go through this standard library example, we can see that we import file system, then we store on a variable called content, and we read a file, which is demo.txt that I have here with a hyphen. And then we print the content itself of the file. So if we run this, it will say hi friend, which is the content of the actual file. But if we run it with the -d flag again, we will see here how we first of all load the constant for the standard library string, and then we import this standard library string. So that way the virtual machine knows which standard library needs to load and which members and methods are available for that variable that we are just loading for the virtual machine itself. So this is how many virtual machines are implemented. But since 4 years ago or something like that, LLMs came out, and we have another world of opportunities and another way of building things. So basically, an LLM, everyone here knows what is an LLM, but basically it's an AI model that based on an input, it generates autoregressively another output that makes sense semantically. So here in this example, for example, the quick brown fox jumps over, it could generate D based on the previous context of the previous generated tokens. And this is great for generating text without any sense. But we could use this, for example, for running autonomously the virtual machine itself. So we could use how the element generates text to connect to the virtual machine execution itself. So in this case, for example, we could say, okay, if I had a program that performs load const, and addition, I could let the LLM try to generate the next bytecode step, let's say. The problem is that these are bytes. So how we can make the LLM try to build an execution based on bytes, since the LLM is not trained on bytes itself, or at least not raw bytes. It's trained on semantics of natural language. So I was thinking of this problem so many days, and I came that maybe we should try to generate execution based on the standard library itself. So the LLM, instead of generating code or generating bytecode for running the virtual machine, it could generate bytecode. It could generate a standard library calls that then will be compiled to bytecode. or it will call the bytecode itself. So in this case, for example, the LLM could generate http.get, then get path.current working directory, and then write a file for that request performed, and then continue generating different execution. So to make this, we need a way to let the LLM know how our standard library works. So in the virtual machine right now, we have through the whole standard library, we have implemented these kind of definitions that here is on the file system example, but we have this kind of definition where we say which is the name of the member of the library, the description of what it performs. In this case, with the full text of a file returns a string, and the path is a local relative path. And also we gave the LLM the params that it needs to fill to perform that call or that standard library call. So let's see also how this autonomy demo, let's say, works by the LLM. So there are two autonomy ways. First of all, there is one that if we only use the VM like binary, we can say anything here. For example, write a test.txt file with hello world, let's say, and it will call the LLM, generate a plan, and based on this plan, start using the standard library of the virtual machine itself to generate an execution. In this case, it says successfully wrote hello world to test, and it says hello world here. This is great because right now, since we control the whole flow of execution, we could say how the LLM interacts with our virtual machine. So this is thanks to the AI module, which is basically part of the standard library of the virtual machine, which implements many things, but the principal thing that implements that let us do this kind of execution is the run agent method. Basically, the run agent generates a plan, iterates over a plan steps, then iterates over each step, generating different actions to achieving that step, let's say, and then it gives us a summary and also a result based on the whole execution. So if we take a look to this code, which is basically the run agent stuff, basically here returns an agent summary and it starts by creating a plan, sending, because everything is sent by events through the virtual machine, so it starts generating a plan, sending that the plan started, also building a virtual machine or agent context, counting the errors and steps, and we start with the outer loop, which is the whole plan steps that the LLM generates, and we say that we start with a step. We also count like if the step has been done, and also how many iterations do we have inside of the inner loop. Sorry, inside of the inner loop. So inside of the inner loop, we have a max counter, a constant to avoid the virtual machine keeps going through iterations and consuming, for example, tokens. And if it performs more than those iterations, the virtual machine says that the execution failed. And let's increment the inner iterations if that's not the case. So on each step, we generate on each step we generate a step, which basically means generating an action. This action is a standard library call that lets us, as we have seen here, to perform a task. In this case, file system.write file. Once we have this action, we say to the whole virtual machine that we just generate an action and we execute that action. We will talk about how this is not dangerous for our machines. But for example, let's trust that this doesn't make anything harm to our machine. So it generates a result and then increments the step and returns the action result. If we make this through the whole plan that the LLM generates, we finally will get a step done field which let us close the loop, both loops, and generate a summary for the whole execution and returning the value. So this will be simplifying the whole loop that let us work with this kind of stuff. So for example, we could say also get the content of creators industries via HTTP and write a file. write a file with it, let's say. And we can see how here performs an HTTP request, how it can recover from errors if something is not well typed. And it says, I fetch the creators industries, and here we could have, so for example, in this case, it understands that the write file doesn't work because the LLM tries to escape the sandbox. So this is why it doesn't, it does not write the file. If we say here, for example, the same, but we say this VS Code version that they just released, it's not working very well for me right now. Okay, so get the content of with it, let's say. This time it's Cloud time, like Cloud responding. I don't know why right now it's saying that. Maybe, well, demo thing, I guess, like demo effect. But basically, we can run this kind of behavior. So, for example, I could say, open a browser and search for Nike store. And since we have a browser standard library here in the virtual machine itself, we could open and start searching for inside of the browser itself. So our virtual machine could go and start doing things as far as we gave, like, the virtual machine possibilities, or we increment the standard library members. If we go back to our Chrome here, we someone could say, so how is this secure, or how we can know that this is not harm, as I say. So, well, we have, through the whole virtual machine, a sandboxed environment that let us, inside of the standard library, import things. For example, if the LLM wants to use a path, it will first pass through this result path with context. So that way, so here inside of the result path with context, we have, for example, which current working directory we'll use. We will enforce a root prefix. We will resolve the symlinks before the LLM tries to write something. If it tries to build a symlink, and then with the symlink try to access out of the sandbox and all this stuff. And also, we, after resolving the symlink, we try to ensure that the root is the same that we enforced previously. So we have all this kind of sandboxed environment that let us believe, let's say, in how it's behaving our virtual machine. Also, great. So here we could say, great, Cristian, but here we are running this virtual machine on a CLI-like mode. Like, how is this actually compiled to the virtual machine? Because you just told me that this is a standard library. So where is this library, or how can I use it through the bytecode, let's say? So here we have an example, the run agent example. This run agent basically give us we have the AI module that give us the run agent method, which basically was this one right here. So we could import AI and then say, AI run agent. We let the AI, like, we give a call to this run agent, and we set an end condition, and we give an agent control. All of this is compiled to actual bytecode that we just have seen with the previous examples of the Ego files that are executed by our Rust virtual machine. So if we run this, we will see how we will get the same behavior as the previous one, but we are controlling how the LLM works inside our virtual machine. And here we can see raw execution or raw actions. So this is because we provide our run engine method written in Rust, which is this one, a way of deciding when the LLMs can continue or cannot. So this run engine method has the whole system for deciding when it will end or will not end. And here we can inspect, for example, which module wants to call, which member is accessing, with which arguments, let's say. So we gave the virtual machine the whole control, but we let the LLM tries to execute things, and the virtual machine decides which things can be executed or not. So we are always trying to play a game of orchestration autonomously, but also secure with some kind of security, and not only trying to say, hey, I accept this task or I accept this action. So I strongly believe that in the next years, we are going to see this kind of virtual machines evolving, where we trust how the LLMs can behave autonomously without us trying to say, I try the machine, I try the AI God. Like it will not harm my computer, and it will not like remove everything recursively of my root. So I'm saying this, but anyone could say, Cristian, but you are saying this, but you didn't try anything that can like expose something real. For example, I have here a sandbox example, which is the same as this run agent, but basically tries to read the file outside of the sandbox. Because by default, our virtual machine sandboxes the current working directory. So it cannot escape this current working directory. So here we could say also run agent to read this file, and the same as before. So we could run this sandbox. Sandbox. And here the LLM tries to perform a task, which is read file of this file, and it says, I'm going to read the file. But if we try to cut this file, it exists. And if we take a look to this code, it's trying to access on a good way, let's say, because here we could create test.ego and import file system, and tries to read file of this secret, and we could print this value and run this as a bytecode. VM run test.ego -t. And here we can see how it tells us sample secret, and it's the same method that we just have seen that the LLMs try to execute. fs.write file with the same argument, but it cannot read this path. But here, if we build this without autonomous execution, it knows that it can perform that task because it's not sandboxed. So when the virtual machine understands that it's running under an autonomous execution, it performs and it calls the standard library differently. So in this case, it's able to use the sample secret to read, the secret file. And here we can see how we, as I said, we load the constants for the file system, import, and all the stuff. We could also run the sandbox with -d to see how this looks, which is a much bigger program because it's all this file, and basically is loading the AI module, importing. Let me close this. Loading the AI module, loading the AI string, and then importing this AI string with the import operation and all the other stuff. Here we can, for example, declare the function, which is another operation that we have on our virtual machine, and we have all of this behavior encoded on the bytecode for our virtual machine. So this is how we sandbox everything on the virtual machine to let the virtual machine work autonomously through your environment. But we could ask, so why we pick Rust for building this? So first of all, this virtual machine, we can compile it to everywhere. we have this running in desktop, we have this running on Node API, we have this running as a Python library. So we have a whole stack only with one code base, which is very crazy for us, like, to think about it. And also, the virtual machine has many, but many enums. As many of the Rust projects out there, it has many enums. But in this case, the compiler doesn't allow us to keep an arm empty, let's say. So it let us be very secure and be very sure about the virtual machine is handling every case possible out there to avoid the LLM to make bad things on our computer, let's say. So this was everything. We can go through the code base because it will be open source like this or the next week. So we can go through the code base and discuss everything that you want to check, guys. This is why it's more compressed, the presentation part and their part now. And yeah, I'm Cristian, the founder of Creators.
I turned my mic on. Can you hear me?
Yeah, great.
Can you, just a question I can ask here, I think, in case the room can't hear me. There's a lot of different VMs, including WASM and whatever. Can you just describe your motivation for creating this one?
Well, so to be honest, I first started building a programming language in Rust, which was this one. Which was Ego. So this is a very basic project in Rust, which has a parser, a lexer, and the basic stuff for being a programming language. And I made a talk about this in Madrid, Barcelona, in the Code Motion event, which is an European event of programmers. And after building this language, I thought, yeah, but this is a syntax tree based like programming language, and it only travels through the tree. It would be cooler if I can compile this and run everywhere. So that there I started building my own virtual machine. And after reading Machines Can Think from Alan Turing, I thought maybe we could try to add a new operation for the virtual machine to execute itself autonomously. In fact, I didn't put in the presentation, but we have some examples of the virtual machine generating code, Ego code, and then compiling it into bytecode. So that way, for example, if we say we have a struct A that has a property, let's say height and width, tell the LLM, give me, get the property area, and the LLM builds a code in Ego that then compiles to a bytecode with the function that makes that operation. So it generates, it's like meta-programming of the LLM inside of the virtual machine compiling to the bytecode. So that way you ensure that the bytecode is safe. So it's like very experimental thing that we're playing with. I think I have here if I can open Discord in like safely. Yeah. So let me copy a code so that way I can show you what I'm talking about. I wasn't thinking about presenting this part of the meta program because it was very experimental, but basically it's this. We could create here a new file, for example, which basically is an struct of a house with different properties. And here we access one property, but also we could access a property that doesn't exist. And the LLM, if knows that doesn't exist, will try to build the Ego code for performing that task. In this case, is making a multiplication between the height and the width. So if we run this, and I hope it works because I didn't try this before the talk. If we make VM run exp, the height is 4, total area is 20. And we don't have this hard-coded anywhere, and like in any part. So this is, I didn't make like the whole login, but this is compiled into a temporal file that then it's written on a temporal file, and then it's compiled to an actual bytecode that runs the virtual machine. So that way you can also, after, check if the code was correct, also have some kind of caching. So if the LLM fails, you can go back to the already compiled bytecode. So we're working on this kind of stuff that is not like very canonical or traditional, let's say. So this is what motivates me to build this virtual machine.
Speakers on if anybody has a question.
Yeah, any other question? All right. Oh, one more question.
Yeah, I have a question. The role of the virtual machine seems very powerful because it's a way to take something that's semi-trusted, like your LLM, let it execute a whole lot of work of its own volition in a safe environment. When you get to the point where that work might involve running other programs, do you have ideas about how you would sandbox other programs if it wants to run a system utility that doesn't know how to run in your VM?
I think that's a whole problem by itself. I probably think that in the future, so I'm too young, so I'm 21, so I didn't get to this point of computer science. But years before, we didn't have floating point as part of a CPU architecture, for example. So then later on, we said, okay, so every computer should have this implemented by default. So I think that in the future, probably when the LLMs can run more powerfully on less space, let's say, I think that we will have a way to abstracting this as a service like the USB, for example, interface. So we will say like call autonomous and will run on your computer autonomously with everything sandboxed by itself. But I think that we are not there right now. Like we have this whole limitation of the 2 nanometer things and how LLMs become and how we can make them fit on a small CPU and all this stuff. But I think that on the future, maybe in 5 years or 10 years, I don't know, we'll have some kind of interfaces, probably written in Rust, that let us communicate with some parts of the hardware that actually ensures this kind of security for our computers.
Cool. All right, any other questions for Cristian? Okay, thank you very much. Wonderful.
Thanks to you guys for the space.
Anytime, and yeah, maybe we'll reciprocate the idea of doing talks. Rust Barcelona, love your logo, by the way.
Thanks. So I will stop sharing the screen.
Thank you very much. That was great. All right, let's take 10 minutes, and then we'll be back for Jack.
Who on the speakers?
You can keep them if you want. I'm not reliable at coming here.
Some kind of like that.
At least it did in pitch. You know, the linkable conference kind of speakers might be interesting. Because they have the built-in
I don't know what's. I mean, we usually have the room speaker hooked up.
Yeah, the AV is broken. Yeah,
So we're worse off than usual.
and a more technical remote.
Yeah.
And it has a train that comes right next door.
Yeah, so Seattle people can make it.
That's why we picked it. So those are all the reasons. You nailed it.
We're not really stationed at the capital because I'm pretty far in South County, so I came here much earlier.
Okay.
The capital county.
Yeah. Yeah. Very cool. Very cool.
Camp.
Yep. That's what I sometimes do.
Closes at 5, and I was like, it was actually closing. That was Apple Maps lying.
That's great. That's great. Yeah, that's exactly the reason why we like to come here. And
And I see the C++ meeting also means here. So
yeah, we're actually good friends with them.
And a joint meeting last year.
Yeah, we had a joint meeting last year, and
Also, so we could pick on D.
and Walter Bright is a member of the C++ group, and so when we pick on D, like he's right there. So it's really funny. But he's a good sport. He's a very good sport.
I have a colleague of mine that goes on just graduated recently and
How was he? How was he as a lecturer?
She had no complaints.
Really?
Hi, Carl.
She thought it was interesting.
Carl?
That's surprising.
Carl, can you hear me?
Oh, this is
Christian. Vaya, fue curioso.
Checking things.
And then join meeting, I guess.
Yes.
Brad, I don't know if your slides had.
And share screen.
Oh, it did? I just tweeted out.
Ideally, just entire screen to avoid any possible
Do you remember? It's always the third.
confusion. All right, Infinity Tunnel, great.
I see it. I'm still seeing the recording icon. So.
This is going to be a talk about the K-hand summation algorithm that Scott just shared in the Discord channel. If anybody's Scott, can you? Yeah, he's not even listening. Never mind. That's a joke. That's not what this talk is about. Obviously, this is too small for anyone to read, but is that kind of, it's like plausible, right? Is that a plausible size of text? And then if I'm in here, maybe we just sort of bump that up a few. We'll see. We'll see. You know, fine. Okay.
So he had all this.
Oops. Sorry, no, the wrong thing.
So I have one of the radio stuff. I've done from them. It costs like 15K. That's awesome. And I was like, I have a lot of friends who really like radio stuff. Oh no, this was like at least fully stacked. Like all kinds of digital protocols or whatever. No, this was like years ago.
You might even get Jack in the Box.
I'm sorry. Oh,
This camera.
is that my own? I'm still in the meeting? Or is that, no, that's me on your laptop.
Yes.
Okay. I was like, I thought I turned my camera off, actually.
It's still watching me.
Like, disconcerting.
Cristian changed his name to underscore because that was the shortest thing we could find that wouldn't block his picture in the meeting on the side. Because whenever he did a name, it was,
No reply dev. It would like cover his. Wow, that's funny.
So we are going to get Cristian in a box for his video.
Nice. All right, are you ready to go?
Ready as I'll ever be.
Okay, well, that sounds good.
Am I talking to this, but that's not for the room.
This is for the 90.
I'll still want to hold something for the room.
If they can't hear you.
I can project. I can project.
Yeah.
Either way, the recording doesn't care.
Yeah.
All right, everyone. Jack is ready to give us a. I forgot the exact title. I know it's to do with async.
Yeah, they're making progress on AsyncIterators.
Yeah, making progress on AsyncIterators. All right, take it away, Jack. Want the mic?
I think I don't need the mic. Okay. You guys can hear me clearly if I talk like this, and this microphone will pick me up online. So I think we're good. So, folks who know me know that I've been on this kind of obsession for like a year. There's this category of deadlocks in async Rust that I think is bad, that I would like to fix. And what I bring to you,
that they're good.
the features are in the eye of the beholder, right? It's one man's trash. So what I bring to you today is a draft RFC that I would like to submit as an actual RFC at like some point in the near future. An RFC is a request for comments. That means that's a proposal in lots of different fields or languages or whatever, and it's a proposal in Rust. So when you want to make a big proposal for changing Rust, you submit an RFC, and there's a Git repo. I think Scott has probably done it. I don't know. Great. I haven't. So this is a draft RFC. I would like at some point to submit it as an RFC. And my hope is to talk to you about it today. Thank you for letting me jibber jabber. I worry this is just like a very poor fit for a talk. Raise your hand if you've never written any async Rust at all. So, okay, about half the room. I apologize to all of you in advance. I met Anton on the way in. He is coming to Rust. He's like day zero of Rust. I am going to be just absolutely terrible host to you, Anton, and I apologize. That said, C# does have async, and you may have used that. And so probably some reasoning by analogy would be possible here. I haven't used async in C# since 2010, which I think was when it was invented or something. Maybe I can. Anyway. So anyway, this is a document. I put it in the Discord channel. So if you want to read it, it's in the meetings, the hashtag meetings. It is long. It is somewhat dense. It goes into a number of like very technical digressions about things like how generator syntax will work and a bunch of stuff that we're not going to talk about. And so like this is, you can read it, but like you like probably won't, want to, like, it's fine. So I'm gonna, I admit it is a stretch to try to, talk about this here with you. So thank you for letting me try. Out of curiosity, has anyone in the room ever looked at the stream trait in async Rust?
I think.
Okay, 3 hands. Okay. So we can spend some time talking about how async iteration works in Rust at all today. And then I can show you a deadlock that comes up that I think is somewhat surprising when we play with async Rust, iteration in async Rust. And I can talk about my proposal for fixing it. I think that I can maybe just like I'll throw that on the screen at the beginning and then maybe again at the end, and we can just kind of look at that. And maybe most of what's actually useful here will just be like talking about how async iteration works at all. We're gonna kind of have to see how we feel, and hopefully people have questions for me or some sort of more interactive. In fact, I thought I even see a hand moving.
How is this connected to the cancellation deadlock that we did, or is it not at all connected to that?
You want to repeat the question, and I'll run around.
Sure. So yes, the question was how is this related to the you called it the cancellation deadlock? Yeah. So a previous talk of mine was called Never Snooze a Future, and cancellation does not generally cause deadlocks, but snoozing does. And so this is another example of snoozing. So that's the next question. So this is in the broad category of things you can do in async Rust that deadlock you that I think should be illegal. This is an example, and this is sort of how it happens in loops. Is kind of how you could think about this particular case. So just to put the most important detail up front, this is what the async iterator trait looks like today. Is that vaguely big enough? Maybe you should zoom in. Yeah. So this is what the async iterator trait looks like today. The subtlety here, which you will run face first into if you ever try to use async iteration in Rust, is that this trait only exists on nightly. This is an unstable trait. And that means that nothing in the ecosystem actually uses this trait. Everything in the ecosystem uses a trait from the futures crate, which is very popular. And the trait is called stream. And there's actually a big debate about whether this should be called stream or async iterator, and I don't care. But so the stream trait, which everyone actually uses, looks identical to this. This just happens to be what it's called in the standard library, and maybe eventually what it will be called if it is eventually stable. And the important thing is the poll next method. So those of you who've never looked at the future trait, again, I apologize. I'm kind of assuming a lot of background here, but when we have a future in async Rust and we want to drive it / ask whether it's done / get its value if it's done, we call the poll method. So poll next is in the same vein. But of course, this is for an iterator, not just a future. So a future will give us one value, maybe eventually, whereas an iterator is, we're supposed to be able to get like many values from it. We're supposed to be able to loop over it, right? So the idea with poll next is that it can give you a value, and then you can keep calling it and get more values, maybe, and then maybe it can tell you that it's done. So just raise your hand if you have seen the iterator trait, the regular Rust iterator trait. Most of the room, incredible. So I think most of the room knows that the iterator trait has a next method and it returns option, right? And it returns none when it is out of items. You're not going to get any more. Similar idea here. You can see that there is an option here. So like the regular next method, poll next is going to return this. The option part of its return value will be some if it has something to give you, and it'll be none when it's saying I don't have anything to give you ever again. But that is wrapped in this poll enum, which is the thing that future poll returns. So that the future poll can say, here's the value, I'm done, or it can say like I'm not ready yet. Keep trying. And there's all this wake up machinery that we don't need to necessarily talk about. So this is a poll of an option. So in addition to being able to say like here's an item or there's no more items, it can say I don't have an item for you yet. That's the whole async thing, right? Is like I'm not going to block your thread. I'm just going to tell you that you need to like poll me more later. Any questions about that? including and especially from folks who don't know how async works in Rust. I see Brad. He does know how async works in Rust.
I have a question. As I'm holding this mic, so it's very handy. If it doesn't have, I've never even thought about this before, but if the iterator, the async iterator, doesn't yet have an item for the next thing I'm about to call, can I call pull next twice and then get 2 pull option self items and await them both?
So you said if the async iterator does not have anything to give me
Yet.
So if let me just, we'll start off and then I'll get a clarification from you. So if I call pull next, if it doesn't have anything to give me, it's going to return the pending variant of pull. I can pull this up. So the pull enum is, so that everybody's seeing the same thing. The pull enum has 2 variants, ready and pending. And so if it has nothing to give me, it's going to return pending. So you're saying.
Then I call it again
immediately.
I call it the
pull
async
next.
iterator again immediately. So
Yeah.
I have 2 of them sitting around.
So you have 2 iterators, or you call pull next twice on the same
one iterator,
One
but I
iterator.
call pull next
Yeah,
twice.
so you will almost certainly, unless it happened to come up with an item in that microsecond, you will almost certainly just get pending twice.
I see. So I could be holding a whole bunch of items that will all eventually potentially go to none if
I
that's how they
don't know
resolve.
what you mean by
I think
holding
you can await
items.
the pending, but it's just a value.
The pull next is going to return a value to me. And so it's going to return a pull option T, right?
Yes.
So if I'm holding a pull option T
Uh-huh.
and I'm not holding it, but I go back to my iterator. and keep
Carl is right
hammering
about the
iterator,
misconception.
Do I get a whole bunch
Yeah,
of...
we got to back up. So this is not a thing that you pull. What we're looking at is the return value of polling. And beyond that, I don't know how to connect with what you were saying.
I think because it's pinned, the content is not moved if it's pending, but after it's returning ready, then it's moved, so you can't call it again.
The async iterator is something you pull and then you get back this pull struct. It's not something you await. You don't await this. I think that's.
We might want to look at
I think his
example.
question is, does getting back a pending imply any commitment on behalf of the thing that gave you that pull result? And I think the answer is no. It's just saying I've got nothing now. I might never have anything if I call
It's true.
pull next 10 times and it's only ever going to be able to give me 9 things. It's not a commitment to give me 10. Is that
Thank
right?
you. Okay, no, that answers my question. So I think the answer was that the return value of the pull next is not a commitment from the iterator about you're getting an item or there's 3 items pending or anything like that. It's just telling
Thank
you
you.
right now, I've
Yes.
got nothing for you.
There's nothing for you
Check
right- yeah.
again if you want.
There's nothing for you right now.
Got it.
It does mean that the iterator is obliged to have arranged wake-ups. That's sort of a standard thing in all of async, is if you get pending, that means wake-ups have happened or will happen. That is still true here. But yes, it could be that then when you eventually wake up and pull it again, it's like, actually, I have nothing. Absolutely. That's correct. So that is pull next. And I realize for a lot of folks, it's sort of unclear how any of this sort of what gets wired up. And as with future, we very, very rarely call the future pull method ourselves. We almost always like await a future, right? And like pull is being called for us. And it's sort of the same story here. We can look at some code that works today. So this is just to have something on the screen, just to see some code run. So if I run this, it's just going to print the numbers like 0 through 10, right? Okay, so it's printing a number every second. So that's the intuition for what's going to happen here. And we can see that we get some ints. This is, of course, just a range. It's not really doing any real work, but we have a range. And this is a little adapter function that turns that range into what the futures crate calls a stream, or what we might call an async iterator. So it just wraps it. Sort of like taking a vec and turning it into an iterator. Same thing here. So just total demo stuff. And then to have this do anything interesting at all, we use the then comment. It's sort of like map. In async land, there's often there is a map function, but it doesn't take an async closure. It takes a regular closure. So if you want it the async version, it's then. I don't know how we're going to ultimately name these things. It's a little bit much, honestly. But if we want the async closure, and we do in this case, it's then. And that's what's going to let me do this async sleep in the closure. If this was not an async closure, I would not be able to do the async sleep. And this is async main, so I would better do an async sleep and not a regular one. Happy to take questions about that if there are any. That's a whole other can of worms. But so this is again, it's not doing any real work. We have 10 integers and we're sleeping 1 second for each one, and we're going to loop over them. And so today, the way we do that is unfortunately a little bit unergonomic. It's a little bit annoying. It's annoying in a couple of ways. First, we have to pin the iterator, which is yet another can of worms. We really prefer not to have to do that. It's not the end of the world, but it is a big paper cut. And then there is not a for loop we can use with async iterators on stable today. There is a nightly syntax, and we'll actually see it on the next little tab. So there is such a thing as a for-await loop. This does actually run. This is a slop fork of Rust and Tokyo. So this will be the glorious future that is not where we live today. We live here. So we have this pinned async iterator, and we call not poll next. Again, this is confusing, but async is often like this. But this other thing, which is called next. Where does that come from? I could look it up. Stream next. So the stream, it's not even in the stream trait. It's in the stream extension trait for reasons. And this next method returns a future. So it's an async method. Poll next is not what you would call an async function or async method. It's a lower level thing. This is an async function. We call that, and that, as with any other async function, okay, we await that. So now we're seeing it get wired up. And just because the for loop syntax is not stable, we use while let. So this async function next is returning an actual normal option, sort of dealing with all that poll stuff under the covers, and it's giving us an option eventually, or not. It might return, well, actually it's an option either way, but it might be none. And we're just driving that loop. Again, this is what works today. There's obviously no deadlock here. This ran fine. There's not even any locks in this program. Well, other than there's not any locks in this program. And this is just to see some code on the screen. Any questions about this? Yes.
So I don't know how relevant this is to this example that I don't know how relevant this is to the example you're thinking about, but if I do next twice and get A and B, and then
are you awaiting them both, or you're not awaiting them?
I await B before I
okay, so you got the
A.
futures. Okay.
Will it get them in the correct order? That's what I'm
that will be a borrow checker error. So if you look at the method here, it takes ref mute self. It's actually quite interesting that it doesn't take like pin ref mute self. Like the whole question of this. The spoiler alert. Like I actually am going to propose that we ultimately deprecate this whole method. It's not standard, so luckily there's nothing officially to deprecate. But yeah, so that you just won't be able to do that. If you were to drop A, the first feature you grabbed, you could then call B. And actually, the question of what exactly happens when you cancel next is really important to this question of deadlock. We'll get up with that. But on its face, it would be canceled. Yeah.
Cool. Thank you.
Cancellation, yet another like async can of worms. Like again, I know like half the room hasn't heard of it, and I know I'm abusing your trust, and I'm grateful. So that is an example. This again works today. It's like kind of annoying. I mean, no one's like happy that it looks like this today, but it does work. Okay, so and of course in this case, we're just sleeping, right? We're not doing any real work, but like this iterator could be grabbing items from a blocking channel, or maybe going over the network and reading bytes from a website, or who knows, right? It could be doing like real async work. We might be interested in that. We might want to run that under Tokyo. Okay, cool. It does work. So we would like to get to this world. Obviously, we don't want these like nightly features. That's not what we do day to day. But we would like to have this syntax. The first thing to notice is that pin has gone away. This is just as a regular for loop would. This is taking ownership of the async iterator, and so it will pin it internally in some sense that we don't necessarily have to worry about. And then it's just we don't have to do while let. That was kind of annoying. That's for loops do that for us with iterators. We would like for loops to do that for us with async iterators. So this exists on nightly. The main issue, if you ever try to use it, even in demos, is that none of this stuff, the futures, helpers, the Tokyo async iterators and all these extension traits, none of these are wired into the standard async iterator trait. So none of this actually works without like a giant fork of Rust, which is what I have in this tab. But we'll get there someday. But so that's some context for diving into what is now the problem that brings us here today that I want to talk about. So any questions before I do that? Let's look at a deadlock. So yeah, so the deadlock is going to be here. And just to get in the right frame of mind, I just want to look at, I mean, this loop does nothing, but just to get in the right frame of mind, what does this loop mean, right? So my iter is some async iterator struct that implements this trait, and the for loop, just like a regular for loop would be calling next, the for await loop is calling pull next for us. And in this case, I don't care about the items, but if I did care about the items, I would be getting them when pull next returns ready some, and then control would enter the body of the loop. And then in this case, it's calling some other function and awaiting it. And the critical detail to keep in mind here is that while, let's assume that do work here sleeps for a while or does something, it returns pending. That's the thing that futures do when they aren't immediately ready. Let's assume it's not immediately ready, and so this await is pending, and so control is given up for a while, and other things run, maybe, who knows. And so when let's assume this loop is in the main function. When main is getting polled, control is here, and so it's calling poll on whatever future this returned. And while we're waiting for this to be done, nothing is calling poll next on this iterator. And of course, it would be kind of bad if we were calling poll next on this iterator, because control is here, and so we're not like ready for the next item. If my iterator were to just throw another item at us, we don't have like another variable. I mean, maybe we have like this variable, but we certainly couldn't take 2 or 3 items, right? Like, so we're not ready for another item. So it's good that we're not calling poll next, but it causes problems if we start throwing some locks into a loop like this. So let's look at this code. So if you heard my last talk and still consented to come again, thank you. You've seen this function before. I think I called it foo last time, but this is sort of my go-to example of causing deadlocks. Like, what does this function do? All this function does is takes a lock and holds it for 10 milliseconds. We could imagine it's talking to the network or doing something where it has a good reason to take the lock, but I don't care what that is. So this is a little tricky detail here. This is a static lock. So even though it's in the body of the function, it behaves like a global variable. We could move the static lock out in C++ or whatever we would. Because no, we can do either way. So this is a global lock. We lock that lock. It's an async lock. I don't have the imports here, but when we pull up in the playground and run this, we'll see it's like a Tokyo sync mutex. So this function locks it. Does an async sleep, perfectly legal, right, for 10 milliseconds. And then this guard is going to automatically get dropped. Nothing exciting here, but we do have a lock. So, and what do we do with that? So we do some magic. So once is a helper method in the future stream module. It's just going to take a regular future and kind of adapt it into a stream. You can imagine it's like adapting one object into an iterator that yields that object. It has only one item in it. So the once is saying, like, give me an async iterator that gives me just whatever this future ultimately returns, and that'll be an iterator of 1. So it's a very, very trivial little helper here. So we do that twice. So we have 2, of course, as in all these examples, we have 2, count them, actually 3 calls to do work. So 2 of them are pretending to be async iterators correctly. And then we're doing this fun thing. So merge is a combinator that will exist, I believe, on async iterator, but does not exist on regular iterator. So raise your hand if you've heard of iterator zip, which exists in many languages, including Python. Yeah, I think most people have. So like if we have 2 iterators and we want to get an item from each and return them in like a tuple or whatever, that's a zip. Merge is similar, so we're getting items from both, but instead of returning them as a tuple, we're just returning them one by one, and we're returning them as they come. So if one iterator is giving me an item every second, but the other only gives me an item every minute, well, I'm just going to be returning a lot of these over and over again, and then eventually I'll get one of these, and I'm just going to keep doing these. So this is merge. So the idea, merge is not something that we could do with a regular iterator. I mean, you could, I guess you could sort of, if you have 2 iterators and you wanted to get items from that as they come, you could spawn 2 threads and kind of, hand them off and over a channel or something, right? You could do something very fancy. And then, the question of what happens if you break out of that loop, it's like the thread's still running. It's, no, there's a reason we don't do that. But with async code, I mean, this is the kind of thing we expect to be able to do. Right? We expect to be able to join 2 futures and run them concurrently. this is the merge is sort of the iterator version of that. We would like to be able to draw from two async iterators concurrently. If they're both like that, what did I call it? Future stream iter. If they're both just like a range, if they're not actually waiting for anything, then I don't know. I'll probably just alternate. Who cares? And all the items will come out very quickly. But if they're actually blocking, then I'm waiting on both of them, and whichever one gives me an item next is going to be the next item out of my iter. So that's merge. Merge is great, and we hope that someday all of this is stable and we can merge async iterators. That would be lovely. But that introduces concurrency into this example. So we have a lock, and we have concurrent iterators. And so we start the loop, right? And we get the first item. So you can imagine what's going to happen here is that, we can imagine that merge is probably going to pull this guy first. Sometimes the implementations try to flip a coin or something, but I don't think this one does. So the first, let's see, the first one, the first do work that gets pulled, it's going to get that lock successfully because nothing has touched it before. It's going to start its sleep. And then that sleep is going to be pending. So the first guy is going to return pending to the merge, and then this other guy is also going to get pulled, but he's going to block here, right? Because that lock is taken by the left side. So we're going to wait for 10 milliseconds. And some wake-up machinery will happen, and then the merge, we're inside of the for wait. The merge is going to pull the first guy again. The first guy's going to say, like, yes, my sleep is finished. I will return. I will unlock the lock. In this case, my return value is like unit, nothing, right? Paren. The items in this iterator are just nothing, but that's fine. So after the sleep, the first do work guy, the first like once iterator that wraps him yields an item, and then control enters the body of the loop. Right. So where is this guy? Is the key question. Is this guy is kind of still here? We haven't merge hasn't gone and pulled him again yet. He's still here. And then we get to this body, and I decide to call do work again. And you can see exactly what happens. This guy is going to wind up here. It's going to block on the same lock. There's a slightly funny detail here where it turns out that when the second guy blocked on the lock, he took a place in line. It's a fair mutex. That's not a critical detail, but in this case, it is a fair mutex. So the second guy here is holding a spot. So our third guy gets in line behind him. But the second guy never gets pulled again. So remember we were just looking at the 3-line trivial example. When we're in the body, we're not calling pull next on the iterator. So nothing is ever going to drive this guy ever again until we get to the end of the iteration of the loop. And we're not going to do that because this guy's trying to take a lock. Questions?
Why wouldn't, when the first guy unlocks the mutex, wouldn't that send some sort of signal which would wake up the second one to keep going?
So yes. So when the first guy unlocks the mutex, the machinery of what will happen here, the nuts and bolts are useful and interesting. The second guy has registered a waker on that mutex. And so when the first guy unlocks that mutex, it invokes that waker. And so the merge it's a little funny. It's like the merge is going to return an item, but a waker has been invoked. And so control is going to move in here. This guy is going to yield pending because he's not going to succeed again in the guard. And then the fact that we invoked a waker earlier means that main will in fact immediately get repolled. There will be no waiting for any sleep. And we'll just end up polling this guy again and making no further progress. So there is a waker there. Yes. And when we see how, I haven't even talked about it in detail, when we see how poll progress is going to fix this, that waker is critical. But right now, that waker is basically it's not getting dropped on the floor. We're polling something, but we're not polling the thing that waker wanted us to poll. And that is actually critical. I realized that was kind of a lot of junk. But,
why is the fairness of the mutex not critical?
It's that's a good question. That's fair. So it is critical insofar as if you stuff an unfair mutex into this demo, it no longer deadlocks. But the reason I call it not important is that if we had do work here, do like sleep, release the lock, and then sleep a little bit more, then an unfair mutex would also deadlock this. What you would need is you need this guy to like acquire some sort of exclusive resource. And with the fair mutex, it sort of already got it just by trying to lock the lock. With an unfair mutex, we would need to let it actually lock the lock. But we're perfectly within our rights to do whatever like extra sleeping is necessary to kind of make it happen that way. So I call it an uninteresting distinction. It's a little bit self-serving. Brad.
I guess I'm a little confused about two things. I tend to avoid async like the plague, except for in Missy because they made it simple, because it's not fearless for exactly the reason you're talking about. So I actually very much enjoy this because it feels like this is why I don't program in C++ anymore, right? But I'm confused about two things. I thought that you would have to poll again in order to advance a future.
Yes.
Even if the waker got information that says you may now make progress,
Right. Somebody has to
you
poll.
still have to poll
Yes.
again.
Mhm.
And then the second thing was, I'm surprised that the polling that does happen polls the wrong,
Yeah.
polls guy number 3 and not guy number 2. Can you talk about that a little bit?
Yes. So to your very first observation about how all this is terrifying, I do believe in my heart of hearts that we can get to a place where like the tools catch these mistakes 100% of the time. At least when you're writing async functions. If you're writing impl future, impl async iterator, you're kind of responsible for your own mistakes. But I do think we can get to a good place here. So that I think you're basically just asking me to repeat, like, how is it that we end up polling the wrong thing? And there's kind of two. There's like the reason we do it and then the reason why it's hard to do differently. So the reason we do it is like, if you think about what an async function is doing, like ignoring the loop, it's just like, you food out of wait, bar out of wait, baz out of wait. Like if you're awaiting baz, the future that represents the body of that function, it knows where it is. It has some state that's like, oh yeah, I'm on this await point, right? And so when you poll it, its job is to poll the thing that it's on. Like it knows that it should poll baz. It probably doesn't even have foo anymore, or that member has been destroyed, or that enum doesn't even have that field or something. But it often doesn't even make sense when you look at the level details. But anyway, more importantly, it knows where it is. Like async functions, the futures that represent their bodies, keep track of where control flow is. And so in this case, control flow is here. Like when main is polled, it is its job to poll the do work future. Like that's where it's at. So like we will need to, my draft proposal, we'll need to define an additional responsibility here that says main needs to do more than that. And that's going to be sort of wired into the loop. But the flip side of that coin is, to the extent that myiter only has a poll next method, the only way you can poll it is by at least being willing to take an item. And a for await loop can't like buffer a bunch of items. That's not a reasonable thing for it to do. And so even if we decided to say for await was responsible for calling poll next, we would be causing another problem at the same time. So just to put a bow on this one, we cannot run this on the playground because the playground doesn't have my fork of Rust C. But we can adjust this slightly. Those of us who've played with Iterator a lot know that the for loop is kind of the same as the for each method on Iterator. They do similar things. One just takes a closure, right? And there's a similar story here. So we can open up a playground example. This is the same code, but it's, there's some closure syntax and it's indented, all funny. But this is the for each instead of a for await loop. The body is the same, and I've put in some print statements, and we can run it. And we can see that yes, it is the deadlock that we hoped or feared it would be. So we made it into the body of the loop, printed here. We started waiting on this, and we never get here. So we've got this is I think there's no change here. This is exactly the function we saw before. This is exactly the stream AsyncIterator we saw before. All we changed is how we write the loop, and it deadlocks. So this is real. This is on, you can run this on stable today. So you all have been very patient with me. You have a question?
So the way I'm making sense of it is that semantically what we're asking for here is for each element yielded by this stream or this async iterator, you want to complete the body of the thing before you go on to the next one. And that's the root of the problem here. Like
something like that.
It's like a regular for loop, because that's semantically how those work. Versus like with the then or whatever operator, then you're attaching an async next thing to do for each element yielded, no matter what order it is.
Yeah, so there's a lot of different ways to think about this. It is certainly, like if we imagine the then, like one side is in this case, I don't think I have a then. This one doesn't. The other one did. But we could imagine if we have this then, it's got some async code in its body, it would be quite bad if some combination of merges and loops and locks just paused control in the middle of that body. We don't want that. That's the same snoozing deadlocks we saw with futures, that we've talked about for a year. That's how future lock happens, right? You've just suspended the execution of a body. That's real bad. The closest metaphor. So what I'm not going to show today, but we could, and hopefully, this works on Nightly. There's generator syntax in Rust. So I don't know how many folks in here have seen the yield keyword. It's not stable, but very much like Python, you can just write the yield keyword in an async function. Also in a synchronous gen function, I think it also works. Though there's all sorts of pinning problems with how exactly that will work. It's a little bit better shape in the async world, surprisingly. You can write async gen function and you write async code and it can yield items. That it's amazing if that works. And all the same deadlocks sort of there's a version of them that uses async gen. And so we can think about if the body of an async gen is executing, it would be quite bad if control just like randomly paused on some line. It would be no different from it in any other async function. However, when control reaches the yield, well, at that point, we do expect, the body of the generator, right, same as in Python, right? The control is suspended until the caller asks for another item, and then control re-enters at the yield and proceeds, right? So that's expected. So we are willing, the generator is willing to allow control to pause at the yield, but control should never pause until you reach the yield or an exit. So that's the high level sort of metaphor that might work here. And then there's in the text that I don't encourage everyone to read, there is a table that makes this very concrete in terms of the polling responsibilities. So you get this return from this method. What do you do? And so part of what we're talking about here is this one. No, this one. Well, in a way, both. Maybe more this one. So if you say poll next and it returns pending to you, you do need to keep polling that when it asks for a wake up. And that's not so different from future poll. You need to keep polling it when it's pending and asks for a wake up, or you can cancel it, but you can't just do nothing. So that gets, unfortunately, this contract is substantially more complicated than the future contract. Again, this link is in Discord for brave folks who actually want to read this table. The poll progress, for context, since I do have this up, poll progress has been proposed for several years. This is not a new idea. It's not my idea. Just about the only part of this document that's like genuinely new, I think, is this rule. So if you want to dive into the minutia, this rule here, and then this paragraph elaborating on it, and then this link to the rationale section, that's just quite long. That's what's new here. But yes, that was a rambling answer to your question. So I think if you'll humor me, I have another 10 minutes or so. We can talk about how we can resolve this deadlock. So there, okay. Sorry, resources on the playground. So what can we do here? How are we gonna fix this? That is where poll progress comes in. So the big proposal is that instead of just having poll next, the trait needs to look like this. Small detail out of the way first. I do suggest that we change the return type here instead of poll of option. I think it would be better to have a 3-part enum because the contract is actually quite subtle. This is not critical. This all works perfectly fine if this remains poll of option. Poll of option can be one of 3 things. This can also be one of 3 things. They're the same. The critical detail is this. So there's a new method. So poll progress is just another way to drive control, but it doesn't return an item to you. The only thing it can return is it can say, I'm ready and here's nothing. Because you didn't call poll next, you didn't ask for an item. It can say, hey, no further progress can be made. And if you're a trivial iterator, like what did we see before? Future stream iter, like just arrange or whatever, like poll progress will do absolutely nothing. In fact, if you're an async gen function that's not doing anything fancy and concurrent, poll progress will do absolutely nothing. But if you're looping over other iterators and they may have concurrency on the inside, poll progress needs to be forwarded in such a way where it can do its work. Let's just run it. So I do have this terminal. All it's going to do is run. This is going to be a really anticlimactic demo, but this is the same code, and it's just running on my fork of Rust-C that has changed the AsyncIterator trait to include the poll progress method and has updated for wait loops to call it in the right place. And lo and behold, like it runs. Right. So we print 21, 21, 24. So we loop twice through the loop. Yeah, oh my God, it ran. And like conceptually, like what happened here? It's like, so we like control enters the body, and this guy is going to try to acquire the lock. He's going to fail. He's going to return pending. And so like one of the key points of the contract here is on the way out. So the for-await loop is going to say, I mean, the rule is like the for-await loop is going to call pull progress at this time. So before it yields pending from its body, it's going to call pull progress. That sort of obvious that that's what we want it to do. The rule that we're going to say justifies that is that when you pull an iterator, if it gives an item to you, you have to keep polling it. And if you want more items, you can call pull next again. That's basically how they work today. When pull next returns an item, it's not going to register any wake ups. So if you don't keep polling it, it's like I don't know, it's up for interpretation, but you have to keep polling it. So if you want more items, for example, if there was nothing in the body, or if nothing was pending in the body, we would just run this loop very quickly, and we would just keep pull next, pull next, pull next. That's great. If you don't want to call pull next again because you have something else to do, you then at that time have to call pull progress. That's what the contract will say. That's the rule. And the way the for-await loop will satisfy that rule is it will say like, okay, I'm going to start running my body, and if that body is pending, that means I'm not going to call pull next again immediately. I'm going to wait for this thing. Then at that time, I call pull progress. So you can sort of view it at different layers of abstraction, but that's what's going to happen. So we're going to call pull progress. That's going to call pull progress on merge, and critical implementation detail here that you can get into all the details, schmetails if you want, but merge has a choice. We could say that merge should call pull progress on its two children, or we could say that merge should call pull next on its two children. And I think it actually does end up being somewhat important that merge ends up calling pull next, at least on the right side here. In fact, I think only on the right side here. So the left side just yielded. We don't necessarily want to drive control further on the left side. We will call pull progress on it because it might forward it. In this case, that's a no op. I realize I'm going fast, but we're going to call pull next here. And that's kind of what we were getting at, you and me, Benny, before. It's that we are agreeing that from the perspective of like a generator, for example, these are not generators, but from the perspective of a generator, we're saying like, we promise we will drive control to a yield, and control on this side has not been driven to a yield. And so we will keep calling pull next until it yields. So that means that merge is going to have one buffer slot for an item. That's fine. It can have one field. And so when we call pull progress on the way out after the first time this guy blocks, it will call pull next on this guy. And if we go back up, we'll remind ourselves that, okay, what will that mean? And it'll try to lock the lock again. It will succeed because the first guy dropped it right before yielding an item. And then it'll begin its sleep. So it's not going to exit. It's not going to yield an item, but it will make some progress. And then that sleep will, of course, register a wake up. And then later, that wake up will cause main to get pulled again. As we were talking about, it's keeping track of where control is. Control is here. Main will try to pull do work again. It will fail again to acquire the lock. But it will call pull progress again on the way out. And that time, the right side do work will finish its sleep, return, invoke the waker that's stashed on the mutex, and cause main to get pulled again, which will finally allow this do work to finish. So that's a lot of that's a lot of basketballs in the air, and it's like you are with it. It's perfectly fair for you to think I just randomly drew a bunch of lines on a whiteboard, but the point is that all of that behavior that I just described follows from a relatively short list of rules, and those rules say things like honor wake ups when they're requested, and don't suspend control in the middle of a body or something. So that's what's happening here.
So if this machinery is in the for-await loop, what happens on this fork if you call myIter.pull next and then do work.await and then pull next again?
Well, now you've asked a very tricky question, because so how do you want me to call pull next? It's sort of like saying you sort of like saying you have an async function, you got a future from it, you're going to call pull on that future. It's like, well, if you are yourself an async function, you can do that by awaiting it. If you want to do something lower level, you have to tell me what you want me to do, because a lot of the things you might suggest are things I'm going to suggest should be banned. That for some context, literally, part of the reason this is tricky is that in the body of an async function, you don't see the context argument that poll takes all over the place. So if you want to call one of these poll functions, you have to kind of do this roundabout thing where you like write a future that's going to call it for you. It's a little bit of a gymnastics.
So the answer is you should await instead, and then have it work.
Well, await is not a that applies to futures, right? So if you try to await an async iterator, that doesn't compile. So you can loop over it. This is a very pointed and important question. What do we actually support doing to async iterators? So you can loop over it. You can use any combinator that takes ownership of it. So I mean, the for each combinator takes ownership, but that's just another way to do a loop. You can also use the collect combinator. You could imagine a combinator that takes ownership and returns the first element. I'm going to propose, and this is maybe the most controversial part of this whole thing, that calling the next function, which is one of the ways you could achieve the thing that you just said, should be banned. Like we should not have this function in its current form. So the next function, it requires you to pin the thing. It basically takes a reference to the thing. I mean, this is another deadlock, right? And we can, at this point, we've all seen enough to maybe be able to kind of puzzle through why this deadlocks. So it's really no different from being in the body of the for-await loop. In this case, there is no for-await loop, so nothing would ever call poll progress here. We deadlock for exactly the same reason. In the for-await loop, we can introduce poll progress and fix it. Here, there's no obvious way to fix it. The next future had a reference to my iter. It used it to produce this item that we threw on the ground. It then disappeared into thin air and was never heard from again. No one is talking to my iter here. So I'm going to propose that we nuke this from orbit. That is very controversial for several reasons, one of which is that next is the only way we currently loop over streams today. So of course, these simple use cases can be replaced with a for-await loop. That's great. There are more complicated use cases. What we can do is we can add some somewhat more complicated helpers. I'm running towards the end of my time, so maybe this is a great question. So this can be the last idea. Who's seen standard thread scope before? It's a fun one. There's like a fun old story from Rust 1.0 about how they had to change that at the last minute. So standard thread scope, if you may have, if you've tried to spawn a thread in Rust, you have noticed, if you haven't tried to spawn a thread in Rust, you should, it's fun. You may notice that if you try to borrow local variables in thread spawn, they won't compile. And that's a whole, you can write a book about that. I mean, there's a lot of ideas that go into that. Standard thread scope is the really cool magic trick that makes that sort of thing compile. So you call this function, you give it a closure, it gives you a magic scope object, and then you can spawn threads, and the lifetimes are just kind of work out. It's very cool. We can do something like that with Next. So I don't have it in the RFC. I'm not proposing we standardize anything like this. But I have this repo that currently only runs on my fork, where we define a function that looks like this. So think of this as standard thread scope. So it's like you've passed some closure to this thing, and you're going to do your work in the body of that closure. You've also given it ownership of your stream. It gives you a handle that supports a next method. And the crucial difference here is if you cancel that, this whole thing, all this machinery will keep driving that iterator to a yield point in the background concurrently. It will also wire up poll progress correctly. So if you call, for example, there's deadlock here. Oh, look, the same deadlock, surprise. If you call, this works. So it's very similar here. So we're using the same while let style loop because in this context we have next. We're doing the thing that would normally cause a deadlock here. We need poll progress to break us out of this deadlock. So this machinery that owns the stream is going to be responsible for calling poll progress in that case. So if this whole body yields pending, which is it will certainly do on this line, then just like the for-await loop, this guy is responsible for calling poll progress on the way out. So this is a lot, and nobody wants to pull in a crate just so that they can write their loops. I expect this to be very controversial, but we can have next, we just can't have it the old way. So for code that's doing very subtle stuff with select and Also, some of that I think should be banned, but like I think select is cool, and in its appropriate use cases is cool. And you're selecting on next a bunch of things. You can still do that, but you will need to wire things up appropriately with a helper like this. So this is probably a good stopping point. I see a question from Brad though. Feel free. Yeah.
There's a bunch of questions in the queue here.
Oh, incredible. Yeah.
A lot of basketballs in the air. This is true. I have a lot
Yeah,
of
that's
questions. I'm going to
so
boil
guilty.
it down to one thing I heard. I want to ask one question. You said that we're going to have a slot for the merge because we're going to go to the right.
Yes, merge
that
needs
merge
one
will-
item slot for.
That assumes a binary tree.
Yes.
It's left and right.
Yes.
What about an iterator tree?
Yes. Excellent question. So, for example, you might be referring to something that merges many things together, like futures unordered. So you can, I mean, in this case, it's just two, but you can stuff as many as you want in there, right? Yeah. So that one of the results of the contract will be saying that futures unordered does need buffer space for an item from every future that it's running. It needs to be able to drive them. I mean, their future is not iterators, so it needs to be able to drive them to ready. And so that is some space overhead that it doesn't have to pay today. Now, of course, futures unordered already has like a VEC on the inside that holds all the futures. So this is not a catastrophe for futures unordered. And merge is going to be perfectly no standard compatible. It's just a field.
My question is, you said recall poll progress on the way out.
Yes.
And my question
We're not breaking the loop. We're yielding pending from the middle of the loop body. That's what I meant by the way out.
Okay, so there's some rule by which, like, if the inner is pending, as you're unwinding that recursion, you're also polling progress on the neighbor futures and stuff. In a sense,
I don't want to. Neighbor futures doesn't sound right. This is really only going to apply to for loops over async iterators and things like that really fancy drive next guy. But other, I mean, if you're saying food out of wait, bar out of wait, Baz out of wait, I mean, those guys are dead and gone by the time that Baz gives you pending.
so it's really only a thing for like for async.
It's really this loop. Yeah.
Okay. But like, so every time you get a pending from the body of that loop, you're going to poll progress on
This guy on the way out.
Okay.
Yes. Yes. And the goal of that table and all the rules is to generalize that to any combinators doing all sorts of fancy things. What exactly are the rules? That's when the table's there. But basically poll progress on the way out. Yeah. That's the goal.
Thank you.
Question from online, if anybody can hear me.
I can hear you. Yeah.
Excellent. Kind of more of a higher level or philosophical question. Do you think that the current implementation of futures as it exists in the Rust standard library is the right one for modeling completion-based APIs? As I mean, the original implementation was written mostly to target ePoll and similar polling implementations. Since then, IOURIG has come on the scene, and Windows I think has a completion-based API. Completion-based APIs is also the way forward in WebAssembly.
IOURIG. Do you mind if I repeat your philosophical question for the room?
Please.
The laptop speakers aren't great, but yeah. So the question is the underlying future trait still the right idea? And we could consider that a very academic question because changing that would be very difficult at this point. And I'll admit that I've talked to some people who know more than me, who've worked on future stuff much longer than I have. Some of them think it's the wrong thing, and some of them think there's nothing wrong with it. So there's different opinions here. There's not a right answer, and my answer is certainly not like the right answer necessarily. However, I think the future trait is fine. I think it works just fine. It is not a problem, as I understand it, to use a future to represent IOURIG or IOCP completion IO. There are problems with that, and some of the Tokyo rewrite traits are not the right shape for that. I don't think future has a problem with that. The idea that you might ask a future whether the IO is done is not an impedance mismatch with the fact that the IO is happening in the background. there are high-level abstract questions about whether we could have arranged wake-ups and tracked metadata in different ways to make certain patterns more efficient. I wouldn't categorically rule it out, but I think the design we have is pretty good. And especially if you consider that we need to support embedded, no standard environments, and we need almost all of this stuff to work in those environments, very hard to do better than the future trait we have. The AsyncIterator trait needs to change. That's what the RFC is going to be about.
Right.
I see one more question back.
Yeah,
if we have time,
thank
right?
you. Very interesting talk.
Thank you.
So if I'm following along correctly, it seems like the reason that we can get a deadlock in this example is that the mechanism that allows the wake up of that second iterator that's waiting for a lock is separate and out of band relative to the mechanism that wakes up the loop to say you can now proceed to run your first iteration. That the first one is probably a few texts deep in the operating system, and the second one is like the Tokyo event loop. Is that
no? There's no separation quite like that. So we could grab the whiteboard maybe after and draw it. In this case, I mean, everything's in these examples, everything's just sleeping. So it's all the Tokyo timer backend and wakers, and there's a mutex.
Okay.
Yeah.
I don't need the mic because I'm close enough to this one. Rust is not async deadlock safe.
Is that a question?
Is that true? Right?
A deadlock safe is not a term of art, so you're going to have to tell me exactly what you want. But
you're showing us that we're not safe from deadlocks if we just write async Rust. Are you showing us that maybe we could be, that there is this notion where we could have safe async, where safe now means no deadlocks?
I got
you
your
have
idea.
to say unsafe if we want
I got your question.
to do the low level stuff.
And as I think Carl knows, safe Rust is perfectly willing to let you deadlock yourself if you feel like it. If you just like lock the same mutex twice in a row, you just deadlock yourself. Congratulations. And async Rust is not going to change that. We don't consider deadlocks per se to be unsafe. But the thing that I think is horrifying about this code is I'm gonna go to my original do work. I think I think we should codify this, that we should be able to read the straight line code here, be like, all right, you took a lock, assuming you get that lock, you're not taking any other locks, you're doing a thing that has a finite duration, and then you're unlocking the lock. We should be able to reason that this cannot possibly deadlock with anything. That should be a fair conclusion looking at this code. And in normal threaded synchronous code, that's the conclusion. And like the edge cases that violate that are like stuff that everyone agrees is illegal. Like, oh, you attached a debugger to the process and paused it while it had the lock. It's like, yeah, you unpause it, like, or you killed a thread, right? These things were like, oh yeah, over the decades, we've learned that you just can't do that. Like, we cannot support killing threads. That's not allowed. And similarly, even though canceling futures works surprisingly well, controversial question, it has its problems, but it doesn't have this problem. Canceling futures works surprisingly well. Pausing futures or snoozing futures, the thing that lets this become a deadlock, that has to be totally, I memorized a good vocab word earlier, expicated? No. Purged. Expurgated. Extirpated. Thank you, God. It's not the one that means you spit at the dentist. That's a different. So I do think we can get to a place where that reasoning that I was just talking about, this is not to say that deadlocks are impossible, but like you can reason about them in straight line code. Yes, I think we can get to a place where that works 100% of the time in async functions. We cannot guarantee you don't screw up a future impl when you write it by hand. Impl future, impl AsyncIterator, but this we can.
Just a quick comment about this in case you're not aware of it. I imagine you might be though. RustConf 2024, Joshua Lebo-Fieser gave a talk on what he called X safety. It's something that I'm using for the car project where you can get X safety, so deadlock safety. And actually, I think he demonstrated something that gives you a compile time failure if there's deadlock in your code. And so when you want to be fearless about deadlocks, or you want to be fearless about analog to digital converters, right, doing the right thing when you're doing your steering input on a car, you can extend the type system to actually be compile time safe for these attributes that Rust didn't come with. I thought that was a very fascinating topic, and I wonder if that could serve as a low-level primitive in your domain, such that we could be more lax with the language rules, but the user would simply get a compiler if they didn't adhere to all the things on the checklist.
Yeah, we have to grab a whiteboard and game that out. I think my reaction to that is, yeah, like using the type system to represent your invariants is a good idea. It's good work when you can get it. And it does require you to buy in to use some sort of framework or some sort of pattern, or like we agree we're not going to call standard sync mutex or something like that. Right? But if you buy into that, it's often a great idea. I don't think synchronous Rust is, regular Rust is likely to standardize any particular deadlock-free way of doing things anytime soon. I think databases do it one way and other applications do it a different way. I think there's a lot of different ways to do it. I think the story with async will be similar. Like if you're just talking about normal, like, oops, yeah, I wrote ABBA, that's a deadlock. I don't think we're going to standardize anything in async Rust that'll be designed to help you with that. But I mean, surprise me.
All right, well, thank you very much. What an interesting topic.
Thanks, y'all.
Okay, so that wraps our talks for today, or that wraps our meeting for August. Just by show of hands, just because they always ask us when we show up, who is considering coming to Red Robin? I see 1, 2, 3, 4, 5, 6, 7, 8, 9. And anyone who needs a ride, we're doing 10. So, okay, then we know what to tell them. Thanks, everyone.